Good morning, folks. This is the computer-aided engineering course, and I delivered my lecture earlier today. So this is the recorded version of that lecture. In the first lecture, I mentioned that the first 20 minutes of the presentation was devoted to discussing the course syllabus, but I'm not going to do that in this recording. So if you're interested in the syllabus, it's posted on Brightspace, and you can go ahead and find out what your responsibilities are, how the course is going to be assessed, etc. So, first of all, I want to welcome you back, and then I'm not going to discuss the syllabus as I pointed out. My first problem is going to be the analysis of a bent rod. So I want to remind you that when you took your advanced engineering design, you use the mechanical design toolbar in or application in CATIA in order to create a part, maybe surfaces, do sketching, and then assembly design, etc. So we're not going to discuss that. This is not the course in CATIA, but we're going to be doing at least the first 6 weeks of the course is going to be analysis and simulation, which means essentially finite element analysis. Okay. So let me show you in a couple of slides what I'm referring to. In the CATIA interface, if you go to top left corner and you scroll down, you're going to come across analysis and simulation, and there's two applications buried inside of that. One of them is called generative structure analysis, which is the bare bones things that you need for simple meshes in order to analyze them. But if you have something complicated and you have to spend time on creating a very good mesh, then probably you need to do it in advanced meshing tools. And we're going to use a little bit of that later on. Okay. These are the main things that we're going. These are the main toolbars that we're going to be using in generative structure analysis, and at least for the case for the next 3 weeks, where we go 3 or 4 weeks, we're going to be analyzing only parts, not assemblies. This is pretty much what you need. Okay, so here you see the measure, and then the restraints, clamp, surface slider, advanced or not advanced, but user-defined restraint. And you see the load, for example, pressure, load, gravity, etc. And then you run the calculation with this thing, which is called actually compute. It looks like a calculator to me. And then you do post-processing by going to image and plot the deformation, plot stresses, plot deflection. Before you run that, of course, these are all dim. It looks like that because you don't have any results to show. Okay, my first problem is going to be taking this geometry. We assume that it's made, for example, out of some material, let's say steel. We're going to see what it is later on. The bottom of it is clamp, and that top face, notice that is the top face that I'm talking about. I'm not talking about the edge. Top face is loaded in the way that you see. Now remember, in this course, it's really easy to generate color, good-looking colors, but these colors may be completely wrong. The numbers may be completely wrong. For example, you might ask yourself, is how am I applying a load of 2000, a load, a concentrated load, or a load on that face? Well, it may not be either possible, or it may not be as it's shown. It could be that you attach a rope and you pull the rope by a load of 2,000 pounds, but that's not what this is saying. So these are assumptions that we make. For example, the bottom can be completely clamped. That is an assumption. There's no way you can completely clamp. Clamp meaning that any point on that bottom circle is not going to go anywhere. How are we going to do that? Etc. But these are the load that we assume and the restraint that we assume, and we're going to model them. So most of this course is about showing you how things done. And although I talk about whether these things make sense or not, in reality, how you apply such restraint or loads may not be, well, it's not the job of this particular course. Okay. Now, I want to remind you that the particular problem that you're looking at was done in your stress analysis class as a bent rod problem, and you did this thing based on energy methods, okay? and you created a geometry like that, and then the bottom of it is clamped, and a load is into the page as at this point. Now, this vertical piece goes through both bending and torsion, and this horizontal piece goes only through bending type deformation. This is how you did this problem in your third year stress analysis class. You wrote the energy, uh, uh, basically energy content of that vertical piece based on bending, and this one based on bending and torsion, and add them up and then minimize it, etc., which was called Castigliano's theorem, or you took its derivative in a certain direction. Anyway, that's not the job of this course. What we and later on we're going to solve this problem as a beam problem, but not now. In another week or so. So what I'm going to do is I'm going to assume that this is made out of steel. Here's the Young's modulus of steel, Poisson ratio 0.3, and that load is 2,000 pounds. Okay. Now, the idea behind finite element is to take this, for example, three-dimensional object and break it up into little pieces, little elements. The elements can be the less sophisticated one, which is like a tetrahedral here. You can see that with 4 nodes, obviously four faces, or it can be a more sophisticated version, more accurate version of it, which is parabolic, 10 nodes, and again 4 faces. Okay. And the thing that you have to keep in mind that when you're using solid elements that I'm referring to here, each node has 3 unknowns associated with it, displacement in x, y, and z direction. Okay, so the degrees of freedom associated with each node in a solid element, tetrahedral element, is 3. Okay, we'll see what happens with the beam load or later on shell nodes, shell elements. Okay. Now, a quick reminder, once you find the stresses somehow using a hand calculation or using computer simulation, such as what we're doing, you have to find the stresses, or the software find the stresses for you, and then these stresses, these are components of stress, are put together in an effective expression for stress, which is called the von Mises stress. And this you did in your strength of material, actually stress analysis course this past fall. So anyway, if this thing, for example, exceeds the yield strength, we know the material has yielded, and you may want to safeguard against yielding, for example. If these 6 components of stress, the x, y, z direction or principal direction, there is no shear associated with them, and therefore these last 3 terms are not present, that whole thing reduces to this. And the different failure criteria, one of them is the von Mises failure criteria, which means that your yields, your von Mises stress, effective stress, must be less than the yield strength. Essentially, it tells you that for a 2-dimensional situation, you have to be inside of that ellipse, or it can be a Tresca criteria where you have to be inside of this polygon. Factor of safety is defined as the yield strength divided, or the factor of safety n is equal to yield strength divided by von Mises stress, or if you cross multiply that, this is what you're going to get. So you want to make sure basically that you're depending on what your n is, you have to decide on the acceptable value of von Mises stress. Now, I mentioned in the first slide that symmetry is a big part of this course. Okay? For example, if this load that we're talking about, instead of the direction that I showed you, was in this direction, it's totally unnecessary to solve the problem as the entire geometry. What we can do, we can make a cut through this, take half of it, okay, and solve the problem. Now remember, just cutting it into a half is not the end of the story. That surface that you have introduced, artificial surface that you have introduced by cutting this thing, it has to be put on a surface slider. The same thing here. If the load is upward, there is a plane of symmetry. But if the load is sideways or at an angle, there is no plane of symmetry, and you have to do the whole thing as I'm showing it to you. Okay. Next week, I'm going to show you how to model structures with beam elements. For example, This particular problem is going to be modeled as a wireframe where the cross section is specified to be a circle of a certain dimension. And we're going to do this thing next week. So we're going the only thing that's modeled here is this L-shaped, inverted L-shaped geometry, which is the wireframe of that object. And it's going to be split into, divided into elements. The elements there are just one-dimensional element. And for example, it's impossible to do a problem like that with solid elements, the whole structure, the whole frame as a solid structure. So beam elements are useful for things of this type, or slender members basically, and it's widely used by civil engineers in structural analysis. Okay, so let's go ahead and do the problem. Now, the dimensions of this piece, let me see now. Incidentally, let me see them. This is, I'll go back and forth between this slide and the other one. So 5 inches from here to here, 12 inches from the top to the bottom. Sorry, 8 inches from top to the bottom, from here to here. And the radius of that fillet is 1. You can see that right there. And the circle is, the cross section is a circle of radius 1. So R equal to 1. Very good. Now, we go to CATIA. Now, at least in our university, the first screen that you get by default is the product file. I don't want that because I'm not going to be using assemblies for another 3-4 weeks. So I'm going to close that, start with the part file right here, and I'm going to say part. So this is a part file. And immediately, and I mean immediately, I'm going to save this thing. So file, save management, save as on my desktop. On my desktop, I'm going to create a folder and I'm going to call this thing May 7, and put this part in there. For those of you who came to class this morning, you noticed that at some point the CATIA crashed on me. You should be prepared for that in the lab, and that becomes your your management, skillful management. If it crashes on you, you must have saved your work so that at least you don't lose the whole hour or so, create the part again. This is particularly critical on the exam and quiz days. Okay, so now I have already changed my units. Let me quickly remind you what the units, how to change them. So we go in tools, options. Notice that in this tree, select the parameters and measures and the units tab. In the class, I already changed my units to inches for length, and for force, I also changed that thing to pound. See that? This is how you change it based on this pull down menu. I already did that. And for pressure, now pressure, I forgot to do it in class. Therefore, the stress contour that I got was actually in Pascal. I don't want that. I'm going to change this thing to PSI also. And there is also stress down here that I did change it to PSI in class. So by the way, if you have a hard time finding stuff, you click on the magnitude here on the magnitude tab. It sorts it out alphabetically, and then you go and get your stress. Stress is somewhere down here, right here. And I changed it to PSI, except that even though I did change it here, the legend that I got on the screen was in Pascal. That's why I went and changed the pressure also to PSI. Fine. That's already done. Okay. Now, this geometry, the way I'm going to make it, I'm going to create a circle and not pad it, because if you take a circle and pad it, you get straight bar up. But I'm going to rib it along a curved path. So I'm going to create a circle and then a path for that center curve it's called, and then do the ribbing operation. So let's go ahead and do that. So on that horizontal plane, I will sketch a circle and dimension it. Here is the dimension. Let me remind you where it is. It's in constraints. Here's the dimension. diameter 2, which means it says 2.6, but in my case, it's going to be diameter 2 or radius 1. If you want, you can change this thing to radius, the pull down menu, and then radius of 1. Good. That took care of this. Exit. And then on the vertical plane, on this vertical plane, for example, the YZ plane, we'll sketch the path along which it's going to get ripped. So here's how I'm going to do that. On the profile, I'm going to start here at the center, go up, and make a, instead of making a fillet, what I do is create a circle here, left click down, slightly move, okay? You do it any way you want. You have to create something like that, okay? Let's dimension these things. The dimension is from this to that is 5 inches. And the dimension from this point to that line is 8 inches. This agrees with the geometry that I have on the slide. This is in agreement with these dimensions. Now the only thing is that radius I have to give it. So here is another dimension. Let's move in. That radius is going to be 1. Good. So that's what we've got. We move this thing up so that you can see it there. Now, exit. And here is the rib operation. You see that? This is pad, this is pocket, this is shaft. The rib is right here. Now, notice that right now, this curve is selected. That's if I click on this, I'm going to get a warning message. See that? You see? Anyway, cancel that. Cancel that. So that nothing is selected. You click on the rib. It says, where is the profile? The profile is that circle that you drew. And where's the center curve? The center curve is this thing that I drew. And there we are. Okay. I did all of this in class. The next step was, by the way, let me save this, okay? How do I save it? Because I already put it in that folder. All I have to do is to click on this floppy down here, and it will save it for me or update that geometry that I saved. Now, we're going to apply material. So where is the apply material? It's right there. You see that? Apply material. You click on it. You select the part. And we want it to be made out of steel. This is the metal tab, out of steel. And then say OK. Now, in the class, I wanted to show people what values are used here. So I left double clicked on this, but then the computer crashed on me. That's why I had to, once it crashed, I had not saved it in class, okay? And therefore I had to redo this whole thing, which is not hard, but still it was taking time. So let me save first. Now, I'm going to double click on this and hopefully it won't crash. If it crashes, I hope that it doesn't crash in the lab, okay? So let me try. Double click. It took some time in order to show up. Now let's give it time. Let's give it time. I'm hoping that this will come up, the window will open, and you can change, you can see the numbers and if necessary change it. If it doesn't, don't worry about it. It's the default properties of steel, and hopefully it won't crash in the lab, although I'm not very optimistic. We'll see that. Then I will tell you, based on my other computer that doesn't crash, what the values are used here. I'm pretty sure the Young's modulus is very close to that 30 million psi. It could be it's 29.9 million, and Poisson ratio instead of 0.3, it could be 0.21, etc. If I feel that this is going to cause a problem, because if you double click on it, it crashes, then I'll make sure that on the homework or on the, see, it crashed, unfortunately. I'll talk to our administrator to see whether anything can be done. Otherwise, we use the default properties in the database, material database. Okay, I'm really sorry about this, but nothing I can do until I talk to our administrator. So double click on this. And because I saved it, I can retrieve it. I don't have to redo the whole thing. Okay, say no warm start, no problem. Okay, so let me close that. And we're going to open up that file that I saved. File, I think it must have been this, CATIA part. There we are. So double clicking on this, unfortunately, is not going to give me the value. It just makes the computer crash. It's this particular version of CATIA that certain things will not work, at least on our installation, and we have to be aware of that. And if you break it, you own it on the test. Okay, good. Now, we are pretty much done. We have created the part, we have created the material, applied the material on it, and now we're going to go to the module that you have never been to, analysis and simulation, the generative structure analysis, okay? Analysis and simulation, generative structure analysis. Not the meshing tool because this is a very straightforward problem. So we click on it. What happens is that immediately the interface changes and it tells you, okay, you are in that particular workbench where analysis is done. And we have three options. You can do static analysis or dynamic analysis, basically. Right now, we are doing static analysis. I say this is a default. I say, okay. Now, so what happened here? First of all, notice that the color changed. And the reason the color changed because you put a material on it. Okay, so let me change the material back to no material color. There we are. It's the same thing that you had before. Now, immediately an analysis file is created in anticipation that certain clicks on certain icons, okay, may lead into issues. What I'm going to do is I'm going to save this analysis file. So see, file, save management. Here's the analysis file, save as. In that folder, remember I called it May 7, analysis one. So in case CATIA crashes, at least I have my analysis file because maybe I spent some time meshing it, maybe I spent some time, applying restraint and loads and things like that. If it crashes, I don't want to lose that stuff. Now, let's see what happens. First of all, if you look at the tree, this first item, branch, it says nodes and elements. So this piece is going to be broken down into a lot of elements of the size, okay? Of the size. If you want to see it, if you want to see how it's broken down, you put the cursor on nodes and elements right there, right click, down here, mesh visualization. You click on it and it cautions you that, look, this may take some time. It won't, but in the event that you made a mistake and the size of the element was, for example, of the order of microns, this is going to be a zillion elements in it. It cautions you that, hey, wait, this may take a long time. But that's not the case with me. So you click on it, there we are. You see that? So this is how it's broken down into pieces. Now, the other thing is that if you double click on this, you can actually change the sign, make it smaller, make it bigger, etc. For example, let's see now, this is 0.56. Make this thing 0.2. I'll show you what happens. And then update, basically activate. You see, it's a lot nicer. Let me put it back where it was. Double click, 0.596, remember? 0.596. I'll put it back to where it was. And once again, right click, activate. There you are, ugly. However, if I change the type of the element from linear to parabolic, things will improve. Even though the size is still the same, the shape will be more closely approximated. So right click on the mesh, right click, activate. You see, this, if you think about it, these are curved now. You see that? They're curved actually. When it was linear, it was just flat. So this is better. Still, not very good. But what now I can change the size, for example. I can go back here, either change the size, change the type to linear, put a smaller size, or here, I'm going to make this thing maybe, I'm using parabolic here, point, I don't know, 0.3. 0.3, but the parabolic. Let's activate it. Very nice, much nicer. So don't let it fool you because it's parabolic, these are actually curved. These edges are actually, if it was linear, it would be flat. Okay, very good. So I'll just leave it the way it is. Now, once this is in front of you, there is not really much you can do. You have to get rid of this. You can delete it if you want, or you can deactivate it. That's entirely up to you. So I'm going to say deactivate so that I can do the rest of the problem. Now we're going to fix the bottom of this. This is a restraint that you're talking about, the restraint toolbar. And there is obviously something that you can miss. It says clamp. You select the bottom. Notice that it puts a clamp sign here. You can see that. And we say, okay. So that edge is clamped. Now, every time you do one of these, they are recorded in the tree. So under static case, the clamp is put here. And notice that I can double click on this. It tells me the face was clamped, not the edge. I could have clamped the edge, but that's not the problem that I'm telling you. So good. Now we want to apply a load of 2,000 pounds in this direction. So we go here to the load. Notice that we did apply. This is the model manager, where it was mesh automatically for me. And there is the clamp, restraint. Remember I showed you this uh, slide? Model manager, restraint, load. By the way, the order of these can be reversed. You don't have to do this thing, in that order necessarily. So let's go ahead and do the load. Oops. Let's go ahead and do the load. There's the load. There's the load toolbar. Let me move. Oh, I closed it. You know how to get it back? Accidentally, I didn't mean it. There's two ways to get it back. You go here, tools, uh, sorry, view. You go to view, toolbars, and loads. I accidentally deleted. Oh, it is on, but why is it not showing then? So let me see. Must be somewhere here. Just a second. Let's try it again. View, toolbars, load. So that must be somewhere here. Let's see now. Because I didn't think I was closing it, but it must be somewhere hiding. It must be hiding somewhere. So let's see. There. Accidentally, when I double clicked on it, put it over there. Okay, so let's go ahead and find. Oh, right now it's up here. Let me try again. Double click. It puts it up there, but let's put it down here and double click. Oh, it still puts it up there. Very good. Maybe it was actually put up there. I don't know. I was looking for it. I couldn't find it here, and then okay, it's right here, right there. All right. So here is the force. You select that face in the direction X. Direction X. It has the right number because I did this thing in class. Notice that 2,000 in this direction. If I put, for example, I don't know, also 1,000 component of 1,000 in the Y direction, look what happened. It's at an angle. Yeah, coming out of this plane. You can see that, right? It's coming out of this plane. But that's not what I have. So let me put a zero here, and there we are. Okay. Before I run things, I'm going to save that. All you have to do is to click on the floppy because we already saved the analysis. You click on the floppy and it saves that analysis file. And I mentioned to you why, because if I, for some reason, click on a particular icon that is not working on our installation on this version of CATIA, it crashes. And if it crashes, at least I can go and get that analysis thing and start from there. Let me show you what I mean by that. Suppose I decide to go back to the part right there. You see that part? See that I expanded this part, steel, right there. Okay. If I go to part design, if I double click on this thing, it goes to part design. And remember when I double click on this thing, it crashed. Let's give it another try. Double click, I bet it crashes again. But the good thing is that I saved my analysis. I can go get that analysis and I haven't lost everything. Okay? Yeah, this will crash. I want to show you. You'll just wait. Of course, or I decide to kill the job. That's also a possibility. Because I know that it's going to crash, so why don't I kill the job right now by clicking on this, etc. But I want to show you that this will clash, this will crash, and my work is not wasted. My work is not wasted because I saved it right before uh, doing this. Okay, it's worth it. Give it a try. Hoping that that window will open that I was looking for, but I'm not very optimistic. Let's give it a couple of minutes. There, crashed. Okay, so what does that mean? I go back to CATIA, or I can go to that folder that I had, May 7th, right? May 7th, right there. There we are. I saved my stuff in here. Make sure you know where they are. This is the analysis file. I want to open the analysis. At least I have not lost my load and restraint, etc. And unfortunately, I cannot change the Young's modulus and some of the stuff that I want. Let me, uh, yeah, let me try one more thing before I give up completely. Let me, instead of going here, expanding this and double clicking on that, let me try something else. There is a material here. You see that? This material, see this? See this? Let me double click on it here. It says steel, but unfortunately I cannot open it. That's the problem. Okay. Is there a way that I can open it? I don't think so. Right click. Let me double click on 3D property. Let's see what happened here. Steel. But again, I cannot open this. I took the default properties from steel, which is okay. No problem. All right. This is all done. If you feel that the direction of this is not what you want, you just double click on this thing, put it as minus, and it flips the direction. Of course, in the present problem, it doesn't matter whether you apply 2000 or minus 2000, the thing behaves exactly the same way. All right, so let's go ahead and run it. There is the run. You see this? By the way, since I flipped the direction, hey, might as well save it. Okay, so let's run it. Compute here. Make sure this is on all, because there are other things, but I want on all. And then say okay. And it's going to run very fast. This gives you an estimate of the CPU time that it's going to take on this particular machine. And actually, this, yeah, on this particular machine, etc. So we say fine, and it's done. Finished. Okay. Now we can look at the results. First of all, this icon under the image tool, by the way, it could be that for some reason you may organize these things so that they all go, these things all go in the top row so that you can see top frame right there so that you can see it, you can access it, it doesn't clutter your screen if that's what you want. But anyway, I won't do that. I'll bring this thing out so that you can see the name of this. So image, and there we are. And that's the way it should be. When you apply a load like that in that phase, it should go to the right. And you can animate it. That's the way it should behave. Animation just shows you if there are any gross mistakes. It's not really very analytical in nature. So suppose that you want to know the deflection. So here is put the cursor there on this guy, says displacement. You click on the displacement, it shows you 0.024, okay? Now, what it shows you is all the nodes and the vector with three components, see, which give you the displacement of that node right there. So that means the node at this location has displacement in the x direction of 0.04 inches, negative, of course, and in the y and z direction of 0.0023 and 0.00123. Okay, good. If you don't want to see it in this kind of a rendering, you double click on this, you double click on any of these arrows, say average ISO, not symbol, Average ISO symbol means, of course, here it's an arrow, average ISO. And it's okay, it did it, except that look at the colors like that. So let me change the rendering to down here, rendering, see that? Down here it says, this thing out of the way. Under the view, the rendering is right here, and you use material, shading with material. There we are. Okay. So what it shows you is that the biggest displacement is going to be 0.024 inches. Now, if you insist that you want to see the elements here too, although I don't know why that may be the case, but anyway, then what you can do is you go to that rendering right there. At the very bottom, there is this one with a question mark. You click on it and notice that the elements also show up because the edges and points are selected. So that's fine. Good. Now, incidentally, you can put your cursor on any of these, it'll give you the magnitude of the displacement, 0.02, 0.014, etc. If you want to see the components, then you have to use a different, symbol rendering. Now, this is fine, except that, what about the stresses? So you click on the von Mises stress right here. You see this? Von Mises stress, you click on it. It shows you von Mises stress. Now, in the class, I forgot to change that the units, so the display of the units. So it showed me in Pascal, gigantic number. But here, it shows you the biggest stresses are up here, there and there. And the magnitude of it is 26,000 psi. If we trust these numbers, if we trust these colors and numbers, it's 26,000 psi. The yield strength for, this is 26,000 psi. The yield strength for steel is 30 million psi. No, sorry, not 30 million, 30,000 psi. 30,000 psi. This is 26,000 psi. So if we trust these numbers, we are okay. Now, by the way, notice that if you want to know where actually the location of the maximum is, in this toolbar, which shows you analysis toolbar, there is this icon which shows you big M and little m. It's image extrema. You click on it and you say, okay, it shows you the maximum stress is actually down here. That 26,000 is down here, not over there. Now remember, depending on the relative size of these two, for example, if this is very long, if this guy is very long compared to that arm, the biggest stress is going to be at that location. So remember, garbage in, garbage out. You are responsible for assessing the validity and the fact that these make sense. And I mean, and the only way to know that is what is called mesh sensitivity analysis. Because does this analysis depend on the mesh? If it does, these numbers are totally nonsense. As a matter of fact, let me do the following. Let me go ahead and change the element type. Remember, this was 26,000 over here. Let me change the type of the element to linear, which is the worst element. So let's see what it will give me. If we run it, we have to run it, obviously. The calculator is up here. That's why I put all of these things up there so that I can see them. Say okay. And let's see what the value is now. Any of these things that you plotted is recorded in the tree right there. Activate the von Mises stress. You see? 20,000. So if I had run this, thing, oh, and by the way, where is it at? So let's find out where the location of the maximum is. Down here, you see? If you do, move this thing out of the way, if you do linear analysis, it tells you the maximum stress is 20,000 is down here. Whereas if you do parabolic analysis, it says maximum stress is 26,000 is up there. So how do I know what is right? The only way is to use a better quality mesh and a smaller mesh. Okay, so let's go ahead and put this thing back into parabolic, run it again. Of course, we're going to get 26,000, but I want to show you something. Let's check it out. Yeah, of course it's going to be 26,000 because we already did that right there. Now, suppose I go and change the size of this. I go from zero point 0.3 to point, let's say 1.5, okay? And then we say, okay, still parabolic and run it. Where is that calculator? Right up here. There we are. I want to see smaller size element, almost half of that size. How would it affect the value of the stress? What happens to 26,000 that I had PSI that I had? Okay, let's activate this. Right click activate, 35,000 PSI. Where is it? I'm pretty sure it's up there in that location, right up there. So you see that 26,000? It's definitely better than linear, but it's nonsense. Because when you made the mesh smaller, it showed you 35,000. Okay, yielding. So this is not trustable. 26,000 is not trustable. You have to make this thing smaller and see whether I can trust this number. So let's check it out. So let's check it out. For example, that's what I mean by mesh sensitivity study. If you do a single run and look at the colors here and the numbers, you might as well tear it down and throw it in the garbage can. You have to do mesh conversion study. Okay, let's do one more thing. For example, let me go, if I change the type of this back to linear, which is not as good, I want to see what the effect is. Linear, but small size, run it. I want to see what the effect is on the value of the stress, one meter stress. Okay, let's look at the one meter stress. It shows you 21,000. So definitely, this is not good. Notice that it becomes closer to, when I use a smaller element size, it became linear, it came closer to parabolic. The moral of the story is that these colors can be misleading, these numbers. You have to do a mesh conversion study, make sure that beyond a certain point, the stress does not change that much, and therefore you can take that as an acceptable value, which does not depend on the the uh, on the mesh size. Okay, uh, but keep in mind that the yield strength that I used here for steel was 30,000. If this is a high strength steel, for example, that they use in submarine and ships and things like that, the yield strength is a lot higher. It could be as far as 100,000. Then some of these would have been okay. Okay, be very careful always, and then you save this thing so that if you came back tomorrow, you can open up the analysis file and everything is there. This is so important for the test and the quiz, because what you store is not only the part, you have to give me the part and you have to give me the analysis file. And remember, if there's 3 or 4 problems, these have to be well separated from each other. So you do problem 1, you put part 1 in it, and analysis 1 in it. If there is a problem 2, you can do problem 2 folder, part 2, analysis 2, or give them a meaningful name. All right, folks, so I'm going to stop here. Just a word of caution. I mentioned to you that symmetry is a big part of this problem, part of this course. So if the load is applied like that, and I said use planes of symmetry, if any, then you have to do only half of this, and you cannot leave that face, that extra face that was created alone. When you cut it so that you get half of it, that face that was introduced, that is introduced, you have to put surface slider on it or a roller on it. And what do I mean by a roller? I mean, where is that? There, this is a clamp, this is a surface slider, and there are other stuff here too, but this is a surface slider, which is called a roller in some of the packages. Okay? So that's your first problem. Good luck. And this is the way it's going to be for the next 6 weeks. And then after your midterm, the whole thing is going to change into mechanism design. You're not going to do anything with the stresses and things like that. Good luck.